Hi, my name is Ayan Mukhopadhyay, and I'm going to talk about robust spatial-temporal incident prediction. This is joint work with Milind Tambe's group at Harvard Center for Research on Computation and Society and Yevgeniy Vorobeychik from Washington University at St. Louis. The broad problem that I'm going to talk about is smart emergency response. We want to understand where crimes like poaching, smuggling, human trafficking, illegal fishing, etc. take place, and how we can better allocate resources to combat such issues. What motivates us to look at these problems is that there are several animals like the elephant and the pangolin that are being hunted to extinction. And then there are crimes like illegal fishing that are not only dangerous for the biodiversity of our oceans, but also because they subsume other crimes like child labor. So now there are a lot of reasons why incidents like these happen, but the ones that are of particular relevance to us as computer scientists is that this is a highly imbalanced problem. There are only so many resources that can be deployed to tackle these issues. We really don't know how and where and when these incidents happen. And then there are a bunch of strategic considerations. And the focus of this talk is going to be what the strategic considerations are and how we can alleviate some of these problems. So the problem deals with an area, say, of forests with known places with animal sightings. Now, their forest rangers typically get reports of poaching in some of the areas, and they deploy rangers in order to combat poaching. This is where traditional AI-based and machine learning-based models stop working. However, what happens in practice is that the poachers can simply move to other areas and continue poaching. So the rangers are basically always one step behind in this game, and that's the problem that we want to alleviate. Now, we want to design algorithmic approaches that are robust to such spatial shifts by attackers, which in this case are poachers. So the model we look at is that we assume that we have access to a historical data set of poaching incidents that we represent by T. We consider that the entire spatial area is divided into a set of cells G, and we assume a random variable X that measures some form of incident occurrence. So for example, it could measure the count of incidents in a specific cell and a distribution F that is basically a distribution over the random variable X. And the only thing we assume about F is that it is convex. Most of our approaches are still valid if F is not convex, but there are some optimality guarantees that we cannot provide. Now, the goal of a standard machine learning model would be to find parameters that maximizes the likelihood maximize the likelihood of the function F given the data set. We want to understand how spatial shifts by attackers affect the random variable X. So, for example, if the attacker moves incidents from one cell to the other cell, then the realization of the counts of incidents in the cell would change, for example. We represent all such shifts by the variable S. So, for example, Sij could denote the attacker's choice to shift incident Gi to cell Gj. Now, what the attacker wants to do is that it wants to minimize the likelihood of the model F because it wants these approaches to be inaccurate because typically, deployment of resources is done based on the model F, so the attacker naturally wants it to be inaccurate. The problem with this is, or the problem with us modeling the attacker actions is that we don't really know the true future distribution over the attacker actions. However, what we do is that we use the dataset D as proxy. So we use D to simulate what the attacker would have done if the attacker was planning to do spatial shifts when the attacker was committing the incidents in the dataset D. So the attacker's optimization problem is then it tries to choose parameters S that minimizes the likelihood of the model F, where the random variable X is now affected by the spatial shifts. What the defender tries to do is that it tries to maximize the likelihood of the model, given that the attacker makes the spatial shifts. Now, there are two problems with this approach. First, the inner problem, the attacker's problem, is combinatorial and discrete because the attacker is choosing over a set of spatial actions, spatial locations, and then we have this hierarchy of max and min operators. The way we deal with this, there are two ways that we deal with this. First is called our Scala. We let the attacker choose from all unique modifications that it can make to the dataset. We refer to each unique modification as a chain, and we assume that there are C total chains. So we take the problem, the robust problem, and we look at the inner problem of the attacker, and we replace it by this idea of chains. So we tell the attacker that, sure, you can choose from a bunch of modifications. Why don't you go and pick the one that gives you the maximum utility? Now, that doesn't really help us because of this integrality constraints. The attacker can only choose one chain. But if you notice carefully, then we can actually drop the integrality constraints because the attacker can choose multiple chains only if they give the same utility to the attacker. So now that we have dropped the integrality constraints and we had assumed that f is convex, we can directly use strong duality, and we can replace this problem, the inner problem, with the dual of the problem, which hands us two things. First, it changes the max min into a maximization problem, and it takes this really large number of terms in the objective function, one for each chain, and it puts them in the constraints, which lets us do dynamic constraint generation. So the way our Scala works is that we first take the dual of the attacker problem, and then we keep doing dynamic constraint generation, where each constraint basically represents the attacker's best response against the current defender parameters. So we start with an arbitrary set of parameters for the defender, we get the attacker's best response, we add a constraint, we calculate the defender's parameters again, and we keep repeating. Now, this is guaranteed to converge because there can only be a finite number of constraints, but this is still extremely slow because we still have to solve the optimization problem at each iteration. So the way we deal with that is that we embed the attacker's actions directly into the defender's learning. And we do that by a method called AddDrag, which stands for adversary-based gradient descent. So again, we start with arbitrary defender parameters. We find the best response of the attacker, and we take a gradient step based on the attacker's action, and then we keep repeating this till convergence. Now, there are a bunch of regression models that we show in the paper as to how they fit into our model. Please come to the poster session if you want to know how these regression models work. The evaluation of our experiments was done with data from the Murchison Falls National Park in Uganda. We used 3 years of data for training and 1 year of data for testing. About 18,000 data points, out of which 2,600 showed evidence of poaching. So the way evidence of poaching is collected is that rangers go around the national park, and if they find dead carcass of animals killed by illegal poaching activities or snares, then they mark the specific time frame as having shown an evidence of poaching. We used a bunch of spatial features, topographical features, and animal density features to aid our regression model. Now, there are a bunch of results in the paper. I'll very quickly go over them. So basically, if we don't take spatial shifts explicitly into account versus if we do take them into account, our approach shows a significant improvement in log likelihood in both Poisson regression, logistic regression, and survival analysis, which are the methods we tested. AddDrag is significantly faster than our Scala, which is pretty much the whole point of designing the computationally efficient method. And then finally, we found that the attacker budget is a very crucial hyperparameter. So for example, how do we understand how much of a spatial shift can the attacker make? So there are 4 images in which the leftmost image, we assume that the attacker cannot shift at all. So it's basically a standard regression model. And then for each subsequent image, we increase the attacker's budget by 1 layer. So for example, the attacker can shift to the adjacent cell and then to the cell that is adjacent to it and so on. And we find that if we take too high of an attacker budget, then these robust models start predicting that there is a likelihood of poaching occurring throughout the forest, which is not really crucial. So the attacker budget is a very crucial hyperparameter that must be very carefully chosen using domain expertise. That summarizes the talk. Please come to the poster session if you want to know about the other results from the paper or about the regression models that fit into our robust spatial temporal incident prediction. Thank you.